Each of the problems in section 4.2 is a word problem, and they're not business word problems, these are just geometry word problems. I believe the section has 8 problems, and we're only going to work on problems 1, 3, and 5, which are kind of 3 very similar problems. There's a subtle difference, but it's a subtle difference. And so for each of these problems, I'm going to walk through and follow the same steps. First, I'm going to read the problem to understand what's given and what I'm trying to find out. I'm going to draw a diagram because it's a geometry word problem to match with the wording. I'm going to write down any formulas that I might need, and really it's just going to be the perimeter and area formula for rectangles that we're going to need to get through this section. And then I've structured the problems in such a way that I kind of made like parts A through E, or maybe A through F. And if you just go through and answer the questions step by step, it will lead you to the ultimate answer that I'm going to want for each problem. And I think I'm just going to do problems 2 and 4, and leave you with 1, 3, and 5, which are essentially going to be, twins of problems 2 and 4. And I typed up a solution for 4, so I'll do it first. And let me just get started here and delete a little bit so you can't see what I have typed up. So this is a classic problem that I give all the time. I give this in my college algebra class, and we solve the problem using algebra without calculus, but here we can make the problem a little bit easier. So anyways, I have a campground owner that has 4,000 meters of fencing. He wants to enclose a rectangular field bordering a river. There's no fencing needed along the river. Let W be the width of the field, L be the length of the field. We want to enclose the maximum area possible. So find the dimensions that maximize the enclosed area. This is my goal, to find a length and the width using my 4,000 meters of fencing, constructing 3 sides, and get the maximum area enclosed that's possible. And I suggested to make the width, W, be the sides of the fence that are perpendicular, probably sides of the fence that are perpendicular to the river. And we're going to need 2 widths and 1 length. So now I'm going to start off, and I read through the problem. I understand what's given. What's given is I have 4,000 meters of fencing. That's really the only number that's given. What I need to do is I need to find the length of the rectangle and the width of the rectangle. I'm making a rectangular region that I'm enclosing, and my goal is to maximize the area. So that's what I got when I read through the problem. I know how much fencing I have. I'm creating a rectangular region bounded on 3 sides by fence, 1 side by a river. I need to create 2 widths and 1 length, trying to find the length and the width that will enclose the maximum area, given that I'm only building 3 sides and I'm using the river as 1 side. So immediately, this 4,000 meters of fencing, that's a linear, that's the sum of the 3 sides that I'm constructing, and that's going to be a perimeter equation that's going to be necessary. And since I'm trying to maximize area, I'm going to need to know the area equation for my rectangle. So as I go farther, I drew a diagram, which was actually kind of tough to draw using Word, and this is my stab at drawing this. So I'm going to make and fence in 3 sides of a rectangular region. There's a river on 1 side, and then there's lengths that I make, a single length that I make horizontal parallel to the river, and widths that I make perpendicular to the river. And with my 4,000 meters of fencing, I'm going to build 1 length and 2 widths. So that's a decent enough diagram, the best I can do with my limited ability to work with Word. And so that's kind of the end. I haven't set up anything yet, but this is understanding what's given. I know what I need to find out, and this is a diagram of my situation. Now move on, and now write down any geometrical formula that's going to be needed to solve the problem. Well, I need to know a perimeter formula for the 3 sides of fencing that are being constructed. And very specifically, to get perimeter, you just add up the sides. I'm making 1 length plus 2 widths, and that needs to add up to the perimeter, or the amount of fence that I'm using. I also need to know a generic area formula for a rectangle, and for any rectangle, area is length times width. This, I probably could have written the length that I'm building plus the two widths that I'm building is going to equal to the 4,000 meters of fencing, and it would have been more useful when I get into the problem. But I wanted to make a generic formula here so that when you got into your problem that has a similar question, you can insert the number that you need from your problem for what it's worth. So those are the formulas I'm going to need. One length plus two widths is the 4,000 meters of fencing. My goal is to maximize area, so I need an area for a rectangle, which is length times width. Now we're going to go through and march through the parts that I have asked for this question. I ask the parts in such a way that it's supposed to guide us through the answer. So if I actually read question 4, it would start off with this paragraph or these sentences, and then right under it, it would start out with step A without the other stuff that I have thrown in the mix. In fact, if I looked at like question 2, which I'll do next, it has the problem with the steps to take us to the answer. My goal again is to maximize an enclosed area with a slightly different situation. And now I'm just going to follow the steps. So for part A, I want to write an equation for the length. An equation is a problem that has an equal sign. And when it says write an equation for the length, it implies that I want to have an equation solve for length, equal to something that fits the situation. So question A, in a maybe more precise mathematical way than not, wants me to write an equation that solves for length that uses the information in the problem. Well, the information in the problem is that the length plus two widths are equal to the perimeter, and the perimeter is just the amount of fencing. So my length plus 2W is going to be 4,000. I'm just going to solve this for L by minusing 2W from both sides. And when I minus 2W from both sides, I have flexibility of writing that 2W first or writing it second. And I'm probably consistently inconsistent in terms of what I do. It's probably more proper to write the 2W or the minus 2W, should I say, first. But it's not like a deal breaker if I wrote 4,000 minus 2W. I would call this my answer to part A. This is an equation for the length of the field. It's an equation itself for the variable L that represents the length. When I slide the sheet down to find out what I did, I won't be shocked if I write 4,000 minus 2W. And it would be equally correct. But I did write this answer. That's probably the more correct way to write it, but not such a big deal had I written it differently. So done with part A. Again, these parts A through however we wind up finishing is just to take me step by step so I don't have to think of to the answer of what is the dimensions that maximize the area. So I'm trying to find the value for the length, the value for the width, that when I build those three sides I get the maximum area. So done with part A. I'm going to move on to part B, and I'm going to write an equation for the area of the field. Well, I know this is a rectangle. Even though I'm only building three sides, it's still a four-sided rectangle. One of the sides I'm not building, it's the straight river. Well, so generically, my equation for the area would be length times width, but this isn't going to be good enough. A stands for area, L stands for length, W stands for width. What I'm going to need to do is I'm going to need to get the area equation so it doesn't have two variables to the right of the equal sign. And what I'm going to do is take my answer to part A and change the length in the length times width area equation to that minus 2W plus 4,000. So this is length times width written with only W's and A's, getting one variable deleted. And if I clear this parentheses, I get the area as minus 2W squared plus 4,000 W. That's going to be the answer to part B. When I slide this sheet down, I probably have exactly that written. So that's exactly what I did here. I replaced the length in the equation, which what I found it to be in part A, did the math, there's my area equation. that's going to give us partial credit. It's going to make my work easier to grade on the test. But ultimately, my answer needs to be the length is some number, the width is some number, and I'm probably going to use up all 4,000 meters of fencing. So part C, I'm going to turn this into an absolute maximum problem. So I'm going to create a table that has numbers in the X column, and I need to know some bounds on the width because my area formula right now just has widths in it, and my goal is to maximize the area, and I'm going to find an absolute maximum by creating a table that has 3 values in it: the minimum width possible, the maximum width possible, and any critical number between the minimum and maximum width. And in this problem, because I'm building 2 widths and I have 4,000 meters of fencing, then since I'm building 2 widths of equal size, and I have 4,000 with 4,000 meters of fencing available, well, I know that my width of 0 would be the lowest possible. I don't even know that that's really possible, but if I made a 0, I can't have a width less than 0. And since I'm building two sides, a width of 2,000 would be the maximum width, because if my widths were bigger than 2,000, because I'm making 2 of the sides, it's going to require more than 4,000 meters of fencing. So I just took the maximum, the fencing allowed, and divided it by 2, and that's going to give me the maximum width that's possible. Since I'm building 2 sides, if I made them each 2,000, that would use all 4,000 meters of fencing, wouldn't even allow me the possibility to make a length. Similarly, I wouldn't really even be getting a rectangle if I made the width 0. But to make this into an absolute maximum problem, this is kind of what I need to do to make it kind of fit with the chapter the best we can. So we went through question A, created my equation for the length of the field. Question B, created for the equation for the area. My goal is to maximize the area. So since my goal is to maximize the area, I want to find the absolute maximum for the area equation. And we learned how to find absolute maximums in section 4.1. That's what we're about to do here. So how am I going to find the absolute maximum? Well, I need to know the bounds, and the width has to be between 0 and 2,000. And you could have just written this as in words. You can say the minimum width is 0 meters. The maximum width is 2,000 meters. These are like my endpoints. If I was doing an absolute max and absolute problem from the last section, could have even written like this, maybe 0, 2,000. Anything to let me know that the width has to be more than 0 and less than 2,000. And that's it for part C. For part D, I'm going to get my answer. I have the area equation of, I don't know what the area equation is. I have the area equation of minus 2w squared plus 4,000w. And I'm just going to try to find the absolute max. I'm not going to worry about the absolute min over the interval from 0 to 2,000. This is ultimately what my answer is going to come from. My goal is to find out the length and the width to maximize the area. So let me try to maximize the area. This is an equation for the area. To maximize the area, I'm going to find the derivative and its critical numbers. I'm going to create a table with the critical number that's between 0 and 2,000. And again, with 0 and 2,000, find the y values. Each of the x values is going to be a width. Each of the y values is going to be an area. So part D wants me to get the width. Ultimately, I need the length and the width to get my maximum area, and I want to know what the maximum area is. So how do I find the value of W? Well, this is just like I said, an absolute maximum problem. I'm going to create a table. I'm going to have 0 and 2,000 in the left column because those are the endpoints of the interval that I'm working with. And then I'll add any appropriate first derivative critical numbers, which means I need to find the first derivative. Again, that area function is minus 2w squared plus 4000w. And when we're doing absolute maximums and absolute minimums, we put the endpoints in the interval in a table, and we take the derivative and get my critical number. So the derivative of negative 2w squared is negative 4w. The derivative of 4000w is 4000. I'm going to get the critical numbers by setting the derivative equal to 0. If the critical number is between 0 and 2000, I include it in my table. So I'm going to minus 4000 from each side and get minus 4w equals to minus 4000. And then I'm going to divide both sides by negative 4. And I get a critical number by setting the first derivative equal to 0 of 1000. Because that's between 0 and 2000, I'm going to include it in my table, just like we did in the last section, 4.1. So this is just, this algebra is shown a little bit nicer. So now my table is going to have 0, 1, and 2000 in the X column, and these are the widths. And then in the Y column, this formula, if I put in the number for width, it gives me the corresponding area. So for each value in the X column, I put in the value into the area equation, and then I use my calculator. So I plugged in 0 for the W's, used my calculator and got an area of 0. Plugged in 1000 for the W's and got an area of 2 million square meters, because here the dimensions of the widths, these are linear, it's just going to be in meters. The dimensions of the areas are going to be in square meters, for what that's worth. So here it says at a width of 1000 meters, the area is 2 million square meters. And lastly, I put 2000 in, I use my calculator, and because these right here, they would have either, this would have no width and only length, so it's not really a rectangle, it has an area of 0. This has only widths but no lengths, I think that's how I would say it. And might have those backwards. Yeah, this is only widths but no lengths. And so anyways, the outside ones aren't going to give me the maximum because they're missing one of the dimensions. The best width is going to be 1000 meters. And this is my answer to part D. Part D, I want to find the value of the width that leads to the maximum area. My answer is going to be this x coordinate of the absolute maximum. This is actually the corresponding area that corresponds to the width of 1000. I'm going to need that in the very last part of this. So I'm almost done. Part E wants me to find the corresponding length. So my rectangle, I'm building two lengths, I'm building two widths and one length. I know that the width that I'm going to build is 1000 meters to maximize my area. I even know the area is 2 million square meters. I lastly need to find the length, and I'm just going to use the formula, the length equals minus 2w plus 1000 that I got in part A. And I'm going to take the 1000 and I'm going to plug it in for the width. And when I do that and crunch that number on my calculator, I get the length for the one length that I'm building is 2000 meters. That's just taking the value that I've got for the width, that's going to maximize the area, and plugging it into the length equation that I figured out in part A. And so my answer to part E, which is the length, is 2000 meters. And lastly, it wants me to find the maximum area, and I've already done that in the right-hand column of my absolute maximum. So I could have just stole that, and that's what I've decided to do here. So that's everything for problem 4. Your problem 5 should be a twin to this. I want to do problem 2, which is going to be a twin to your number 1 and 3, I believe. So I'm going to go through the same steps in number 2, and then that'll be the whole video. And you can do 1, 3, and 5. They'll feel just like these two problems. So in problem 2, a campground owner has 5,000 meters of fencing. He wants to enclose a rectangular field with the fence that he has, with no restrictions on having a river. So in this case, instead of making just 3 sides, the campground owner is going to make 4 sides. So when I go to draw my diagram, this is the region that the campground owner is going to enclose. Maybe to keep bears out, who knows what it is. But in this case, we're going to build 2 widths, or 2 lengths, be consistent with myself, and 2 widths, rather than the 1 length and 2 width that we did in the problem with the river. Here there's no river. And I know that to build these 2 lengths plus the 2 widths, I'm going to use up the 5,000 meters of fencing. That's available. So that's kind of the crux of this problem, and my goal is to maximize the area. The equations that I need, I'm going to need a perimeter equation and an area equation. And this rectangle, we're building 4 sides. And so my perimeter is going to be 2 of the lengths plus 2 of the widths, or 2 of the widths plus 2 of the lengths is the amount of fencing that I'm using. And still, this is a generic rectangle. Its area is still just going to be length times width. This is generic. Now I need to improve upon the generic to get it to fit the numbers in the problem. And that's going to be as how I march through parts A, B, C, and D. So for part A, to take an equation and solve it for L, for this particular situation, I'm going to take the 2 widths that I'm building, plus the 2 lengths that I'm building, set them equal to the 5,000 meters of fence that I have, and I'm going to solve for L, and I'm going to be slick here to make my math easier. I'm going to divide through by 2, which is something I'm allowed to do. If a problem has an equal sign and there's a common factor, you can divide it out. So this is going to give me width plus length equals 2,500. And I'm going to emphasize that this width has a 1 in front of it. It's going to make my algebra easier in a minute. So I'm going to minus 1w, or just minus w. I don't really need to have the 1 in front, but quite honestly, I know what's coming up. Having the 1 in front is going to help me in terms of the algebra that I have coming up in the next parts, but I can suppress that 1 for my answer to part A. So my answer to part A, either with or without the negative 1 in front of the w, either negative 1 times w or negative w plus 2,500. This is an equation of the length. It fits the situation and it's solved for length. Done with part A, now we'll move on to part B. It's going to guide me to the answer for the best length and best width to maximize the area. For part B, my goal is to maximize the area, and I'm going to write an equation for the area so I can figure out how to maximize it. And area is just length times width, and just like I did in the previous example, I'm going to change the width to something that's more appropriate. So I'm going to get the area is, I'm going to change the length to something that's more appropriate. The length is negative 1w plus 2,500. So I can change the area equation into area is negative 1w squared plus 2,500w. Again, that 1 in front of the w squared isn't really necessary, but when I do the derivative, it's going to help me not make a mistake. My answer to part B, the formula for the area is negative 1w squared plus 2,500w. Part C wants to just know the bounds on the width, and I'm going to find the maximum and minimum width. For part C, the minimum width is 0. You can't have negative widths. And because I'm building 2 widths, I can't use 5,000 meters to make my widths. I just divide the 2 widths that I'm making, and I get the maximum width is going to be 2,500 meters. In terms of my answer to part C, this is a nice way to write it. I can say the width is in between 0 and 2,500. Can write it like this, 0 comma 2,500, which is kind of more like we would have written in part section 4.1. Or you could just say minimum 0, maximum 2,500, maybe put units of meters in, but I didn't, so that's going to be okay not to have them. So I'm still not really to my goal. My goal is to find the length and the width that maximizes the area, and the next 3 questions will take me to that answer, the real answers that I need. This is all the preliminary stuff that's just going to guide us to the answer. So for part D, I want to maximize the width. How do I maximize the width? Well, I'm going to find an absolute maximum for the area. I want to find the area that maximizes, I want to find the width that maximizes the area. So I came up with an area equation of negative 1w squared plus 2,500w. And I want to find the width that leads to the maximum area. And I'm going to choose 0 and 2,500 for 2 values in my table as I try to find my absolute max. Again, the numbers in the left-hand column are the widths. The numbers in the right-hand column are the areas. I'm going to see if there's any critical numbers between 0 and 2,500 by finding the derivative. I'm going to say the derivative is minus 2w plus 2,500. That's just a simple derivative. This is where I wanted that minus 1, because now I can go minus 2 times w and get that derivative nicely. I'm going to set the derivative equal to 0. I'm going to minus 2,500 from both sides. And then I'm going to divide by minus 2. My critical number is going to be 1,250. And because that's between the 0 and 2,500, I'm good. Now for each x, I'm going to find, or for each w, I'm going to find the corresponding area. So for the top one, I'm going to go negative 1 times 0 squared plus 2,500 times 0. And then I'm going to do negative 1 times 2,500 squared plus 2,500 times 0 times plus 2,500 times 2,500. And for the last row where my answer is going to be, I'm going to do negative 1 times 1,250 squared plus 2,500 times 1,250. And I'm just going to do the bottom row. These two come out to 0. I know from doing so many of these that those always come out 0. You can pull them on, do them on your calculator, but I'm just trying to save a second here. So I'm butting up against 30 minutes. And this is just mindless. Well, heck, let me just do this one. Negative 1 times 0 squared plus 2,500 times 0. That gives me the top y. And then negative 1 times 2,500 squared plus 2,500 times 2,500. It's just mindless. There's another 0. And then lastly, where my answer is going to be negative 1 times 1,250 squared plus 2,500 times 1,250. And that gives me 1,562,500 square meters for the area. This is clearly where the maximum is. And in part D, it just wants the width that gives the maximum area. And so I'm going to write my width as 1,250 meters of fencing. I already know my maximum area, so I know the answer to part F already. The maximum area is 1,562,500. And then areas in square meters. The X's, the units are in meters. The Y's, because they're area, the units are in square meters. So let me just write something. I'll just write out the word square meters. but I could just have written like meters squared for my symbol if I cared to. Almost done with everything. I've got everything I need, but I want to find the dimensions, the length and the width to maximize area. And to find the length, I'm going to use the length formula. So when I go to do part E, I'm going to use the length formula. The length is negative width. The width is 1250, so it's going to be negative 1250. That's just taking the length equation, changing that width to 1250 plus 2500. And if I do that math, I get 1250. So my length is 1250 meters. That is everything for question 2. And quite honestly, when you go through and do problems 1 through 5 in the homework, they should feel just like this. I didn't flash them up on the screen because I didn't have this line, find the dimensions that maximize the enclosed area. For some reason, when I wrote the problems, I forgot to write that line, and I didn't want to show an incomplete problem on the screen, but you can pick those up in your homework. You're not responsible for these fun problems. The maximize the area by taking a square piece of cardboard, cutting corners out and making a box. That's like problems 6, 7, and 8, I think. That you're not responsible for. So if you just do problems 1, 2, 3, and 5, that will be completely adequate for section 4.2. And we just have 2 sections of new material. There's only 4 sections in chapter 4. And then the practice test.